Hey everyone, in this video we're going to talk about basic concepts in thermodynamics, definitions and physical properties, as well as phases, processes, and paths. So to start with, I'm going to draw a system, and the system is whatever is inside of a boundary. Anything outside of the boundary is called the surroundings of our system. So in order to define the three terms that we just wrote down in this simple diagram, we can start with the definition of a system. So the system is a quantity of matter or region chosen for study. Okay, so it's going to be an amount of matter or a region that we choose for study, and we are going to analyze our thermodynamics from this point of view. The surroundings is the region outside of the system. It is usually separated by the boundary as well. So the boundary itself has a slightly more complicated definition because it can be a real or imaginary surface that separates the surroundings and the system. So what this means is that in some cases we're going to be looking at systems that have a real boundary and a real system boundary. Other times we're going to create this boundary out of thin air essentially, and create this boundary so that we can analyze and explain what is happening in terms of a system with an imaginary boundary. So we do this by just creating this imaginary potential boundary. Now, usually these boundaries are considered to have zero thickness so that we don't have to analyze the system at the boundary. The only thing we need to know is our boundary sets for a point or a surface where we can have a constant value for our thermodynamics problems. Now, going into examples of some systems that we've already looked at a little bit and we kind of understand maybe from previous videos on this subject, is one of them is a piston cylinder assembly where we can have some work being done on the piston or some work being done by the piston. So let's say, for example, that we have a piston cylinder assembly. We can set our boundary in red to show what our system would look like. So in terms of what could be happening, so we could have work on the piston or work by the piston. We could also have some heat applied to the system from the outside, and we know that if we add heat to a system, usually the temperature goes up and the pressure would potentially go up as well, which would push the piston up. Another type of system that we can look at is an open system, and an example of an open system, and the simplest example of an open system, is flow through a pipe, for example. So if we have flow through a pipe, we can look at flow through a pipe and look at all the particles going through the pipe, but what is interesting to us is to analyze the system with a certain scope. So not the whole pipe, but maybe we want to look at a section of a pipe. If we want to look at a section of a pipe, what we can do is we can create a boundary shown by the black dotted line where we can have some mass coming in and some mass coming out of the system with that black dotted line. We can also add heat to the system, and we can see that anything that's outside of the dotted line would be the surroundings. Now, the definition of an open system, because we looked at already a closed system on the left here, on the right, we see that we have an open system. An open system is a system for which mass and energy may cross the boundary. So if you look at this, we can see that on the right side, we have mass crossing the boundary and we have heat crossing the boundary. On the left side, we don't have mass crossing the boundary. The mass is stuck there. However, we do have heat going through the boundary. The next few things that we're going to be looking at is some of the definitions that we need to know in order to move forward in our understanding of thermodynamics and really covering all the basic concepts. So the first thing is, what is a physical property, or what is a property? A property is any characteristic that can be quantitatively evaluated. And there's many different examples of what a property is. So anything you can think of that can be measured is usually a property. So some of the examples of the different properties that we deal with in thermodynamics, and there's a lot more, are viscosity, pressure, for example, volume, density, temperature, and mass. And there's many other ones. Now, the important thing about all these values is that we can actually assign a number to these values. So a property is really something that can be evaluated, so it has to have a number. Now, some properties are connected with each other, as we'll see a little bit later. So the values of these properties define a state of a system. So the state is really defined by a number of properties. And we have to understand that we need a certain amount of properties to define a state. So as I'm writing the definition of a state, what I want you to understand is that a state really comes at different points in time. So we could have a state at a certain point in time and then a state at a different point in time. Or it could be a spatial state. So you could have a state at point 1 in your system and a state at point 2 in your system. So we'll look at the two different types of analysis. So in order to understand what's happening, let's take an example of a piston cylinder assembly with some heat added to it. And what we're going to look at is a state 1 before heat is applied and then a state 2 after the heat is applied, and try and understand what's happening. So let's say we add some heat and then we're going to write down all the information that we have before the heat at state 1. So some of the information that we have is that pressure 1 is, for example, equal to 100 kilopascals. Volume 1 could be equal to 1 meters cubed. Temperature 1 could be equal to 300 Kelvin. And then mass 1, we could probably find out later on, but for now we'll leave it as an unknown, and we could also find density 1. Now, after state 1, we go to state 2, and state 2 is after the heat. So what do you think would happen after the heat? Well, one thing that's going to happen in a piston cylinder is that the pressure is going to stay the same. And we know this because the pressure will stay at 100 kilopascals. Now, the volume will increase if you have heat added, and the temperature will also increase. So what happened? Let's try and discuss what happened between the 2 points. Well, what happened is that at state 1, we had the piston at a certain level, and then at state 2, what happened is our piston actually moved up. And we can see that from the change in volume from point 1 to point 2. We saw that the volume increased by 2 times. So you can clearly see from the diagram that the volume increased twice. Now the next thing we want to define is a phase, and it's important not to mix up phase and state. They're two different things and a lot of people will mix those up. So a phase is a quantity of mass that is homogeneous throughout in both chemical composition and physical structure. So what this essentially means is if you think of water, water can exist in 3 different phases. It can exist in a liquid phase, a solid phase, and a gas phase. And sometimes it'll be a mix of the two, which we'll discuss a little bit here and in further videos as well. So one thing that's important is that gas can also be called vapor for water and for different liquid formed at room temperature. But usually you can call them gas or vapor, it's usually equivalent. Now, a system can have multiple phases at once, as said. So let's take an example of this and try and see how a system could have multiple phases at once. So if we take an example of a tank and it's a completely closed off tank, we can then set our boundary to be just inside of the tank wall. And the boundary, remember, is an imaginary thickness. And let's say we add heat to this tank and we have liquid water. Now, if you know from boiling water, what happens is once you start heating water, eventually it'll start to boil. Now, it's not all going to boil at once. It's going to boil in steps. So the thing that could happen is while this is boiling, you might have 50% liquid water and 50% vapor within this tank. So this is a point where, for example, 2 phases can exist at once. Now, the next thing we want to define is a process. So a process is any change that a system undergoes from one state to another. So now we start trying to understand how we go from one state to another. So state 1 to state 2, as in the previous example, for example. Okay, and the process is that step by step from 1 to 2. And this process is also defined by a path. So a path is a series of states through which a system passes. So essentially, while the system is going from state 1 to state 2 in our previous example, it's taking a path to get there. And we can stop anywhere in the middle of that path and record a new state. So there's an infinite number of states between state 1 and state 2, for example. So let's look at another example. Let's look at what piston cylinder device. We're going to put it on its side just to make it easier to analyze. So we can look at the volume on its side essentially. And let's say at state 1, the piston cylinder is going to have air inside it and is going to have a certain pressure, volume, and temperature. So we'll say that it has P1, V1, and T1. And we take this piston cylinder and now we're going to compress the air. So we're going to bring the air and we're going to squeeze it in. So we're going to have to push on the piston somehow. And now we're going to reduce our boundary to a smaller amount, or our system is going to reduce in volume. And now we can record a pressure 2, a volume 2, and a temperature 2. Now, if we were to draw this on a pressure times volume diagram, which is a type of diagram that we're going to use a lot in thermodynamic analysis, we can now map our experiment from 1 to 2 on a PV diagram. And we can look at how the process from 1 to 2 happens. So the bottom is the volume, and you can see we can map it directly to our sideways piston. And we can say that pressure 1 is equal to a certain amount on the graph. Now we know that if we compress a system and if we reduce the volume, what happens to the pressure? The pressure is going to go up. So we know that the pressure is going to go up, and then there's going to be a path between the two. And that path is stopped by any state that we want to put between 1 and 2, we can stop and record the path that it would take. So this is called a PV diagram, and it's going to be very important in your analysis of systems. Now, if we look at state 2 versus state 1, just to summarize, we know that P2 is greater than P1, so pressure 2 is greater than P1, and therefore we also know that volume 2 is less than volume 1, which is shown by the diagram, and usually temperature 2 will be greater than temperature 1. Mass 2 is equal to mass 1 because we haven't changed the mass in the system. The mass of the air in the system, the air couldn't escape. So the process is from state 1 to state 2. So that would be the process. Now the path is the line in which it is achieved. And it's the process through the change essentially. So we're looking at which path it took. And this path is going to be very important when we're trying to calculate the amount of work that we had to do to get from 1 to 2. But we'll talk about this in a future video. Thank you for watching. If you found this video helpful, please give it a thumbs up and subscribe to my channel for more content like this. Don't forget to hit the notification bell to stay updated on my latest videos. And really, your support helps me in creating informative and engaging content. So if you want to learn more about the topic or have suggestions for future videos, please leave a comment down below. And thanks again for watching. We'll see you in the next one in the video series.